Hey, this is a little describer on how to solve this free response question thing here. So here we go. Fruit flies with a wild type phenotype have gray bodies and red eyes. Right? So gray and red. Certain mutations can cause changes to these traits. Mutant flies have a black body, so the black body or cinnabar eyes. To study the genetics of these traits, a researcher crossed a true breeding wild type male fly. So that's gray body and red eyes, crossed with a true breeding female fly with black body and cinnabar eyes. So black and cinnabar. True breeding is code for homozygous, if you don't know. So then all the F1 progeny displayed wild type phenotype. So again, the wild type is gray and red. So when you cross these, you get gray and red-eyed flies. So this suggests to you, and they're not telling you anything about like different gender ratios here. So this should tell you, since all of these F1 here were gray and red, that gray is dominant to black, and that red, sorry. Oh yeah, no, that's right. And that red is dominant to cinnabar, okay? And that they are probably then autosomal, right? So that is the answer to part A here, right? Is that. So when we go look at the rest of this question. So then it says female flies from the F1 generation were crossed. So the F1 generation, let's go back to this a second, right? So you know that all these flies in this F1 generation are going to be heterozygous there and then heterozygous here. Because the only gametes that this parent can make, right, are that, and the only gametes that this parent can make are this right here. So when you cross those, you're going to get this, okay, as that offspring. So these F1 were crossed with, so again, that was heterozygous here and heterozygous here, crossed with true breeding male flies with black bodies. So black bodies and cinnabar eyes is like this. So he is only making these kind of gametes, and these gametes can be made over here, right? Assuming that they are linked. If they were unlinked and they were on two different chromosomes, then you would also get this combination as one, and you'd get this combination as another of the gametes right there. Right? So notice that like this and this and this and this, these are all four different ones here. So if they were independently assorting, then you get these four, right? But if these are linked, then you're only going to probably get these and these black cinnabar ones. And so that when you cross it, so if this is the sperm and these are the ova, then those are the only possible combinations though. So this test cross, they're showing you that the observed number here, the reason I jumped to the linked thing, by the way, is that I just kind of had glanced at this already, and I noticed that the observed number here, I'm not getting a 1-to-1-to-1-to-1 ratio, right? So if you had, this predicted is what if you had independently assorting, if that body color and eye color were on two different chromosomes. But these are the observed values over here. So I don't really need chi-square to tell me like that these differences are probably not due, they probably are not due to chance. They're probably due to this prediction being wrong. And again, this prediction is based on this hypothesis right here of independently assorting. So this most likely is not the case. So describe any conclusions that can be drawn from the results of this F1 test cross, which is what this is what we were showing up here. Like this is the test cross. This is this F1. test cross. Explain the difference between the expected data and the actual numbers observed for the F1 test cross, which yielded this F2 generation up here. This difference is most likely due to the fact that I had this independently assorting hypothesis being incorrect, right? So independent assortment hypothesis, most likely incorrect. So again, the most likely is that they are linked. Okay, so let's go then and look at what's going on here in part C. So the experimental hypothesis used to predict F2 results needs to be changed. Write a revised experimental hypothesis and a null hypothesis for the F1 test cross and calculate a chi-square value. Complete the table above with your revised prediction. Sorry, I got these a little out of order here. So what I want to notice here first, so then this linked is the revised hypothesis, right? And the null hypothesis is always stating that there is no significant difference between my observed and expected values. So I'm going to do that for up here. So to do that, I want to get my total number of flies here, and that total number of flies, if you do that math, is 976 total flies. So of those 976 total flies, right, to get my recombination frequency, right, I think that I'm getting these here. These are the recombinant offspring, and these are the ones that look like the parents. Right? So in order to get these recombinant offspring, I had to get these gametes being formed, right? But remember that the only reason I got these gametes was if there was independent assortment happening, but we said that was not true, and that since there was linkage, you're going to get these primarily, right? You're getting those primarily, so how do I get these? Well, what must have happened is that from some stick diagrams, right, you had gray and red linked together, and then you had black and cinnabar, right? So this is no recombination. But then if you had recombination, your chromosome stick diagram is going to look like this. And keep this black, but then the cinnabar is going to go with black, right? Strike that, sorry. Gray and cinnabar, and then black goes with red. So we had this is the recombination bit down here, right? So this would lead me to getting these two right there, the red with the black. Okay, so of those 976, 89 of them were the recombinants, right? So I'm getting that 89 from here, right? And so this works out to be about a 9.1% frequency of recombination. So I can take that 9.1%, so 9.1% there is going to get me an revised expected here of 44 and 45. It could have been either way. And then these revised here are going to be 444 and 443. So when I do this O minus E quantity squared over E, I'm going to come out with a divided by E, so O minus E squared over E. This chi-square term should come out to be 0.038. This one should be about 0.27, 0.09, and 0.20. So then you sum all those together, right, to get you a chi-square value somewhere around this. Now these numbers might be a little bit off depending on how you rounded, but it's somewhere in here, right, to get your chi-square value. So then you want to take this chi-square value, right, and you want to compare that chi-square value to this chi-square table. So we're going to go here at p.05, and we had 4 phenotypic classes minus 1, that gets us to 3. Right, so we're going to go here, and we need to look at this critical value, right? So our chi-square value again was 0.94, and comparing that to this critical value here, we see that that is less than that 7.82. Right? So then since this chi-square term is chi-square value is less than this critical value here, this allows us to fail to reject the null hypothesis. And you're using this to conclude that any difference between the observed and the expected, most likely due to chance. Chance, sampling error, etc. Right? So then this is another way of saying that the hypothesis of linkage is most likely true. Most likely true. Okay. So that's how you would do that. Let's go back up here and just check to make sure that we're doing it. So we completed the table. We showed you that for C here, and then discussing how the results of this chi-square are used to support your conclusions for B. That is that discussion right down there. Okay. Thanks for listening, and I hope that helps you a little bit. Feel free to pause and go back, and if there are questions or concerns, write those down, ask your peers, and I will see you when I get back. Thanks.